Okay, so in this module, we'll talk about data distributions and Q-learning algorithms. So far, we have looked at overfitting and divergence issues. The other bit in the deadly triad that we started off with is the fact that off-policy distributions can lead to poor performance when combined with bootstrapping and function approximation. Now, function approximation, in a sense, is somewhat needed because we talk about these high-dimensional domains. Let's assume for now that we want to still do bootstrapping, even though we talked about how bootstrapping can be bad with overfitting and can lead to this rank collapse phenomenon that we looked at so far. But let's say we want to still use bootstrapping. Then we can ask the question of which data distributions are actually good. And in particular, we see that the deadly triad is avoided if we use on-policy data distributions because then it does not satisfy one of the conditions here. But are they really much better for Q-learning algorithms? And if not, so if they are, then it's a good thing. We should always use on-policy distributions. If not, then what are the factors that decide which data distributions are actually good for deep Q-learning algorithms? So these are some questions that we'll answer in this module. For this setup, what we'll do is our experimental setup would be simple. We'll still be minimizing the TD error objective where you are regressing to the target value defined by a Q function under some distribution P. And this distribution P is something that we'll choose. So this is a distribution that we'll decide based on like our goal is to basically figure out what the optimal choices for this distribution are. And just as a sort of a notational thing, we define the Shannon entropy of this distribution P as the sum of negative P log P, where this entropy basically measures the uniformity of the distribution, basically. So if the distribution is uniform over all states and actions, then you'll get the highest entropy here. So that's just a quantity we'll use for our discussion next. So, okay. So which data distributions are actually good empirically in deep Q-learning algorithms? So what we did was we did an empirical study to compare a lot of data distributions, and we then sort of on the simple grid world task that we have been talking about, and then we wanted to draw some inference or conclusions from that. So which data distributions did we compare? So we first compared a replay buffer data distribution, which is an off-policy data distribution collected from the mixture of past policies that were generated so far. We compared on-policy data distributions, which is literally take the argmax or the Boltzmann policy corresponding to the current Q function, unroll that in the environment, the distribution we get, that's the data distribution we care about. The optimal policy, which is the data distribution coming from the states that are visited by the optimal policy in the environment. A uniform distribution over all states and actions, so that's a distribution that maximizes the entropy on the last slide, as well as a prioritized distribution that basically is a distribution over PSA such that it puts the highest mass on those state action pairs which have higher TD error values. So at a given iteration, if your TD error is high, you would put mass on those state action pairs. Now, what we plotted in this plot is basically showing it's a scatter plot that shows the weight entropy on the or the entropy of the distribution P that you're using, which is marked as the weight entropy on the x-axis, and the normalized returns of the policy on the y-axis. So the resulting policy, the normalized returns are marked on the y-axis. It's an averaged out run over multiple states. Now observe that the high scoring region, or the region that actually gets a high value of return, which is higher values on the y-axis, actually corresponds to this this region on the x-axis that has a higher entropy of the distribution. So the prioritized distribution and the uniform distribution, they have high entropies, high h of p values, and they actually also have the highest performance. So the replay distribution also has a high performance, but prioritized and uniform are kind of very high. So what is really happening here? So what we really sort of draw a conclusion from this slide is that high entropy weights are good for performance. So if you have a distribution that is sort of more uniform over all state action pairs, that seems to be better here in this grid world example. Also note that this is in the presence of no sampling error, which means that you assume that you have all state action pairs provided to the algorithm. So that also another assumption that it also puts is that that if you know all the state action pairs, then yes, you can compute the uniform distribution, you can compare the prioritized distribution and so on, but you may not have these in practice because you may not be able to sample all state action pairs equally often, because let's say you have an image based domain, how do you even sample all states in that domain? Now, one more interesting question here is that, okay, while uniform is not possible to do in a sampled situation, the fact that replay buffers work better than on-policy distributions here is sort of also very informative, because the Deadly tried what it said was that an off-policy distribution should essentially be worse than the on-policy distribution because on-policy distributions are more stable. But what we find here is literally the opposite, where the off-policy distribution is actually better than the on-policy distribution. So is the reason here that a replay buffer works because it covers more because it is more uniform and leads to better updates over the queue function? That's a question that we don't know exactly the answer to in general, but yes, from this plot on these sets of environments, it does seem like yes, that's the answer. That the replay buffer has more entropy, and higher entropy things generally seem to work better. So there could be something about how higher entropy over the weights or over state distributions is a good thing, and that is not achieved by the on-policy distribution. So what it says really is the replay buffer is good because while it's still off policy, it's kind of higher coverage and it balances off the trade-off of brittleness against narrow distributions. Also note that if you have the deterministic optimal policy, which is pi star in this figure, which is the lowest, which is in the bottom left part of this figure, you'll find that performs the worst and that has the least entropy among all the possible distributions that you see here. So indeed, there is a connection between the brittleness of the solution due to narrow data distributions and the off-policiness of the solution, and the pi star, like the pi star weighting scheme, which means you only weigh up states from the optimal policy, that indeed suffers from both of these issues and performs worst. And certainly the replay buffer bit, it's not always the case that replay buffers work in a sense that if you make replay buffers larger and larger, some empirical studies have shown that they may not always be beneficial beyond a certain size, which means there's a trade-off between off-policiness and the amount of coverage you make, and you need to get that trade-off right. And therefore the size of replay buffers and design of replay buffers may also matter, and that could be a potentially deciding factor for practical algorithms. Okay, so far we've looked at sort of a study that told us that, okay, among a chosen set of distributions, some work because of some reasons and some may not work because of some other reasons, but how can we actually find good data distribution? So one more thing to note here is that, let's say the uniform distribution, a uniform over all states action pair or all state action pairs is not possible because that requires you to first of all have seen all state action pairs. And that certainly will not be the case in a practical problem. So a lot of those distributions are actually, in a sense, oracle distributions, which you haven't seen during training. So how do you find good data distributions then? So that's sort of the next topic that we talk about. So in this setting, we still want to. Okay, so one assumption that we'll make in this setting is that we don't want to alter the data collection strategy. So what we'll do is we'll still assume our typical TQN actor critic style algorithm, where what we'll do is we'll maintain a replay buffer, which is indicated as buffer D in this picture. We'll unroll our current policy in the environment, let it run for a few steps, collect data, put that into the replay buffer, and make the replay buffer be the history of all the experience so far. Use the replay buffer to update the policy, collect more data, put that into the replay buffer again, and so on. So basically, the buffer is storing all data from previous snapshots of policies that you've seen during training so far. So what we talked about in this recent paper is that if you do this kind of on-policy data collection, where what you're doing here is you're unrolling a policy that you learned in the environment, using that to collect trajectories, putting that data into the buffer. If you're using this kind of a scheme to collect data, even if you're maintaining a replay buffer, turns out that this scheme may not be able to correct errors in the queue function. So far what we've been looking at is how good can Q-learning be when you use different distributions. And what we are talking about here is that if you use your current policy or a previous policy to collect data, that may not be good because it may not provide you corrective feedback to correct errors in your queue function. What is corrective feedback? So the corrective feedback is the ability of data collection or data collection schemes to correct errors in the queue function. So to reduce Q minus Q star, where Q star refers to the optimal queue function. So some notion of that. And turns out that when you apply function approximation, which means you are using neural networks, on-policy distributions may not be that good in terms of error correction, because of an issue that we'll talk about next. And this includes replay buffer distributions as well, because replay buffer distributions still are composed of, it's sort of like a mixture of on-policy distributions from different policies in a sense. So this example or this counter example that I'll describe also includes those distributions in them. And what we'll do, or sort of the more concrete thing that we'll discuss here, is that when you do on-policy data collection, that is when you have when you run rollouts from some policy in the environment to collect data, you may fail to collect. You may end up failing to correct errors in target values that are used in the Bellman backup for training the queue function. And unless you correct errors in those target values, you're basically backing up things, but those things that you're backing up are essentially incorrect values. They are garbage values and they're being backed up. So that's why something like this may end up not providing you the right corrective feedback to make your queue function get closer to Q star. And we'll discuss this on a concrete example. So that's coming up next. So let's consider a simple example here. And this example is basically a simple MDP, but with function approximation. So it's this tree MDP where you basically have a tree, you have a binary tree, sort of like a node. So each of the squares or circles you see here are nodes in this tree, or the node or states in this MDP. You have two actions which take you to two different states or two different children of a given state. And you start at the root of this MDP. So you start at the squared node, that's the start state. And what you do is a path in this tree is basically a trajectory that you can traverse in the MDP. I've shown here for three levels trees. You can make them be arbitrary levels, so you can make h levels in this tree. That's perfectly fine, but for sake of visualization, I only made 3 levels in this tree. Now, let's imagine we are doing function approximation. So we have some features of states S1 and S2, which are marked here, which out of which S2 is the leaf node, S1 is the root node, and the features of phi of S1 and phi of S2. Let's assume for now that phi of S1 and phi of S2 are related, which means they are in some sense sort of very close to each other, or something like that, or they're sort of negatives of each other. So anything of that form could happen. And our Q function approximator, what it does is that it multiplies a weight W. And what it does is it computes W transpose phi of S for computing the Q value of a state. So now it's kind of very clear, which is that if your phi of S1 and phi of S2 are related, then the Q values are also related, because your Q values are a same linear transformation, or they're basically computed using the same dot product with the same vector W on top of these features. So QSA values are also related at these two states, which means that if you update something at S1, or if you update the Q function at S1, it'll also change the Q values at S2, because phi of S1 and phi of S2 are related. So when this happens, we call these nodes as being aliased with each other. So what this means is all the nodes that are circular in shape, they're aliased with each other, which means their features are related. And all the nodes that are squared in shape, their features are related among themselves too. So they are aliased with each other. So nodes are aliased with other nodes of the same shape. And secondly, what we'll do is we'll sort of use this notation where red color in the node indicates higher error, where error is Q minus Q star, which is the notion of error that we saw on the previous slide, because that's what we used to define corrective feedback. And if the color in the node is green, that means there is low error, which means Q is close to Q star. So there's a smaller error against Q star in the Q value of that node. And what we'll do is, when there is aliasing, we'll talk about how data distribution would affect solutions, and in particular how on-policy data collection may not give you enough, it may not give you the ability to correct errors in the Q function, especially when aliasing exists in such an MDP. So let's look at how Q-learning operates with on-policy data collection. Again, just to remind us, epsilon k, which is the sort of, which is the error metric that we're considering here, is the absolute value difference between qk minus q star, where k denotes the index or iteration of learning. So it could be the iteration of fitted queue iteration, it could be some checkpoint of dqn, periodic checkpoints of dqn, anything of that form. Now let's consider this tree MDP again. Now at iteration 1, which is the starting iteration, so first of all, Bellman backups would go upwards into the tree, where you would use the value at a lower node, or a node that appears later or downwards in the tree, to compute target values, and use those target values to update nodes that come above that node in the tree. So basically you are propagating information upwards into the tree when you are doing Bellman backups. Now, in the first iteration, you would have incorrect targets on most of those nodes, because the values are just randomly initialized. You might have values that are incorrect, and now those incorrect values at the leaf nodes or the nodes at level 2 would be used for computing target values for training Q functions at the nodes above them. So, for instance, the root node will use target values, or would use Q values at the nodes in level 2 for computing its own target Q value. The nodes at level 2 would use the leaf node values to compute their own target values for training the Q function, and so on. Now, the root node is the most frequent node in the on policy data collection scheme. So if you actually run rollouts in this tree, so a rollout that starts from the root node goes downward in the tree, you'll find that the most frequent node in that rollout is the root node, because that root node appears with one probability in all of those rollouts, whereas all the other nodes will appear with some lesser probability, because you have two decisions to make. You can go either left or right, and so you are dividing your probability mass into these two different branches of the tree, and this will divide up more and more as you go downwards in the tree, and therefore the most frequent nodes in the tree are the root nodes, or the nodes towards the top level, or closer to the root node of the tree. And the nodes that are towards the leaf or closer to the leaf are basically the least frequent in this on policy data distribution. So if you collect data using on policy data collection, and let's imagine for now that you can collect exactly all the states, so you have no sampling error, you can exactly estimate the expected Bellman error under the distribution of the on policy, or under on policy data collection distribution. Then what you're seeing is you'll find that the largest weight in the loss function, in the Bellman error loss function, would come from the state that is the root node, or closer to the root node, whereas the leaf nodes will have the lowest weight in the loss. And the reason just being that you're collecting data with decreasing probabilities over the tree. As you go down, your probability of visiting a node decreases, and therefore you get a lower weight in the loss for that quantity, for the leaf node. So what is happening here really is that you are training for Bellman error minimization on states that are closer to the root, much more than states that are farther away from the root. And there's aliasing. So basically, if there's any sort of conflict between which gradient to use, you are basically providing more mass to the loss function terms that are coming from the root node, or closer to the root node here. And when you're doing that, what you're really doing here is you're regressing the root node values to incorrect target values, because the target values at the other nodes are not corrected. They are just some random initialized values. So you're regressing to them. And what you're missing really is you're missing the error correction ability, which basically would have appeared if you were to correct for the Q values at the lower level nodes, at the leaf of the tree, because those values are the values that needs to be corrected first before you can propagate correct values in the entire MDP system, because the target Q values are coming from lower level nodes, and those target Q values are not corrected because their density in the on policy distribution is very small. So what this sort of means is when you use function approximation and you use on policy distribution, because the nodes that are the sources of error in Q values in the entire MDP are so less frequent in the on policy distribution that their Q values are not corrected. This leads to incorrect targets at nodes at the upper levels of the tree, for which you actually minimize the Bellman error a lot. So essentially what it's saying is that the on-policy distribution puts most mass on states where the targets are so wrong that even if you minimize those Bellman errors, you're not gaining much than being able to actually correct the Q values at nodes where targets need to be corrected first. And so what happens is if you run on policy data collection here and you train Q-learning with it, you'll find that the errors decrease. For instance, the intensity of the red color here decreases, but you'll find, and you'll even get like green colored nodes here, where you find that errors may even increase. So you might not converge to Q star, you may just be oscillating just because your function approximator couples states or aliases states together, and because your data distribution is still sort of most centered at the root, you may not be able to correct the errors or the Q value errors at leaf nodes, or nodes that are actually the causes of the error in the entire system. and so you may not be able to converge to the optimal solution. So what this says is on-policy data collection might lead to sort of very less error correction at the nodes where you actually need error correction, and that may propagate errors in the entire system, entire MDP. So just to summarize this example, on-policy distributions may not correct error for targets due to function approximation aliasing and skewness of the data distribution. These incorrect target values would then induce error at other frequent states during Bellman backups because you are using target values as blind ground truth for training the Q function. And then when you train under the resulting distribution, you may further inhibit error correction at leaf nodes because you're just trying to minimize errors at the root nodes or closer to root nodes against wrong target values. And because those values are aliased with the nodes appearing at the leaf nodes, you may not be able to correct errors at the leaf nodes at all. And this process continues in sort of this bad feedback loop, and that may inhibit the corrective feedback nature of data collection here. So essentially what we find empirically is that if you measure, let's say, the correlation between the visitation of a policy or the data distribution induced by a policy, d pi k of SA during training, and you measure its correlation against qk minus q star, which is the error that we were looking at so far, you find that this correlation is actually, or the change in error could actually be larger, meaning that the policy might visit states. So the policy, the current policy pi k actually visits some states in the MDP, but visiting those states may lead to increased errors, which you can see with the positive correlation between the change in errors epsilon k plus 1 minus epsilon k and d pi k of SA. And that may still not be good, and that is not good because what it's really saying is that you're visiting states, as you saw in this example, you're visiting states, so your density on states are high, but just minimizing Bellman error at those states is not good, and that leads to an increased error in the overall system just because you're not correcting the source of incorrect targets in the MDP. So essentially, on-policy data collection may minimize Bellman error a lot, but it may not be able to correct the errors in the Q function against the optimal Q function Q star, just because it's not minimizing, it's not putting the right amount of weights on states that actually need to be corrected first before you can use them for Bellman backups. So overall error may actually increase just because you're doing on-policy data collection. It may not correct errors. And just as a curiosity exercise, if you're interested, there's this simple MDP where under these conditions with linear function approximation, you will find that such a similar scenario happens. You can actually work it out. So you'll find numbers, you can actually find out the exact error you will find for each of these quantities if you were to run on-policy data collection in this MDP. But I leave that as an exercise. So what does this tell us as a whole? So it tells us that on-policy data collection, while it is sufficient for error correction or convergence in the absence of function approximation, and that's what the Deadly Triad stuff tells us. If you have on-policy data collection, you should be good enough. When you have function approximation, it can be ineffective in error correction. And the reason for this ineffectiveness is because it may not be able to correct the source of incorrect target values or target Q values in the MDP, and that may lead to poor performance on other states, which are actually more frequent. We also saw that more gradient updates under such a distribution may lead to poor features because if you actually end up doing more and more gradient updates on the same data, we saw that due to, let's say, the implicit underparameterization phenomenon or the rank collapse phenomenon that we saw, or due to overfitting, you may just find poor solutions. And this all combined with the fact that you are using a wrong distribution for updating your Q function may just exacerbate the whole issue. And finally, we also saw that entropic distributions can be better, and probably the reason for why they are better is because they are not skewed in this weird way in your MDP, where you pay more attention to states that are closer to the starting state or closer to the root node, and hence you're not able to correct errors at states which are actually the causes of the error. Because with a uniform distribution, you're likely to correct errors at all states equally often, and you might be better. So Therefore, sort of more entropic distributions intuitively can be better. And the final question here is also that can we do better than entropic distributions? And the answer to this question is yes. We can do somewhat better, and we can derive sort of like a more, in some sense, almost like an optimal distribution that works better than entropic distributions. or just uniform distributions. However, I'm not going to that in this lecture, but you should check out some of the recent work which talks about something like that, because that could be better than a uniform distribution or just an entropic distribution for such problems, for error correction in such problems. So that's the end of this module. Thank you.